All right, so today we're going to continue with the divide and conquer strategies. And the example that we started with on last Friday is yet another programming exercise for your next assignment, where we've got the closest pair of points in a Euclidean plane. We're revisiting that problem. So remember that I forget if we actually implemented it or what we did, but the brute force solution was going to be an order n squared algorithm. And as we've already seen, even from practical, small data, this is not at all practical. In fact, for the grader for assignment 4, I intentionally made some large data sets, like 10 million points. So if you've got 10 million points and you're comparing it to 10 million other points, then your 10 million squared is going to be infeasible. It's not going to be, centuries, but it's definitely going to be more than the 5 minutes that you're restricted to on the grader. So we're going to have to figure out a better way of doing this, right? And again, the problem here is that you're given n points in the Euclidean plane, and we want to find the 2 pair of points, the 2 points that are closest to each other. Now, the way that we looked at this on Friday was from a naive divide and conquer strategy, where you divide it into 2 sets, you conquer by recursively finding the 2 closest pair, but then when you come back from the recursion, you have to be very, very careful, right? Again, here is our idea. We've got a whole bunch of points in the Euclidean plane. I'm not even going to draw the y-axis because we could be in, the positive side, we could be in the negative side, we could be like 2/3 over here and 1/3 over there. It doesn't really matter. But I am going to divide this roughly evenly, into 2 parts. This is the left partition, and this is the right partition. So that roughly there are n divided by 2 points over here, and that there are roughly n divided by 2 points over here. Right? And then you can conquer it by continuing to divide this in half, divide it in half over here, divide it in half over here, all the way down until you find you have a set of 2 points, in which case, by definition, that is going to be the 2 closest points. And then you come back from that recursion. Now, suppose that we come back from that recursion and we've got this distance 1, and these are the 2 pairs of points over here in the right partition that are the closest. Well, immediately you can go ahead and say that the distance is going to be the minimum of D1 and D2. That's the minimum distance between breaking those ties. But you've got to be careful, right? What if there's a point really close to this cutoff here, and there's another point really close to this other cutoff over here that straddles that divide, right? And what if the distance there, D3, is less than D, the minimum distance over here, right? So that leads to, okay, well, now we've got to test everything that goes over this dividing line, right? So, for example, for each x in the left partition, we have to compare it for each, never made sure that this is actually working, it is good. For each y in the right partition, then we have to, compute distance between x and y. Right? And then if updated, if that's less, then we found a pair that's closer. But this isn't going to work because this is n divided by 2. This is n divided by 2. So how many comparisons am I making here? N divided by 2 times n divided by 2 is going to be n squared divided by 4, which is going to be order n squared. Now, why does this not bias anything? Well, let's go ahead and think about this overall divide and conquer approach. Let C sub n be the number of comparisons or the number of distance computations or whatever made by this algorithm on a set of n points. Now, the recursion is standard, right? There are 2 recursive calls on inputs that are half as big, right? And there's a non-recursive cost associated with that. This is our non-recursive cost. Now, of course, if we just have to if we just restricted to these 2 points, making a minimum between those, then the non-recursive cost is going to be 1, right? Because we only have to have these two pairs of points, this distance, and all we have to do is take the minimum. But that's not the case. Remember, there could be things that go over this line, meaning that we end up having to do this, giving us an order n squared algorithm for the non-recursive cost. So, n squared. Now, bring in the master theorem that you did on assignment 3. Our A is going to be 2, our B is going to be 2, and our D is going to be 2. So A versus B to the D. What is the inequality here? 2 versus 2 to the squared, so it's going to be greater than. And what case was that? It's case, yeah, I think it's case 3. Implies that C sub n is going to be order n to the log base 2 of 4, right? Or no. Log base 2 of 2, which is 1, but that's not the case 3 is going to be n to the d, which is equal to order n squared, right? In other words, we're right back at square one with our brute force algorithm, okay? So computer science 3 is all about data structures and algorithms. Let's focus on that first part, data structures. Let's focus on the second part of that first part, structures. The computer science and problem solving is all about recognizing and identifying structures so that you can exploit it. In this case, we're not looking for a data structure. We're looking for a structure within the problem itself. In other words, geometry. Is there something that we can bring from our geometric knowledge that allows us to exploit that structure, recognize a structure, so that we can get away without doing so much work? Right? Now the idea here, I'll go ahead and add in a new one here. There we go. All right, so let's think about that, right? Let's zoom in on that partitioning, okay? So here, I'll go ahead and do it in red here. There's the partitioning, and this is the left, and this is the right, okay? Now, the strategy that we described over here was, well, for each element in the left partition, for each element in the right partition. So let's focus on one element in the left partition over there. In other words, one point. Right? I'll do it right here. Now, again, do we need to compare it to every single point in the entire right partition here? Do we need to compare it to a point that's way over here? Right? Remember that the distance here, the minimum distance that we found so far is D. Do we need to compare it to something that's way over here that is going to far exceed D no matter what? No. We only need to focus on one part of this. We only need to focus on, and I'll do it in another color here, green, there we go. I'm going to go ahead and draw another imaginary line over here, right? And another imaginary line over here, eventually, that is distance D from that middle point there, right? Now, do I need to compare it to something over here that is more than distance D away from the cutoff point already? No. I only have to focus on points within this, what I'll call slice. So this is the right slice. And this is the left slice. Okay? So for each point, for each x in the left slice, we don't need to compare everything over here either for the same reason, right? If it's way over here, if it's more than distance D away from the dividing line, it's not going to be any closer to something over here or over here. So for each point in the left slice, all I need to do is concentrate on for each y in the right slice. Right? But that still doesn't buy me everything. Right? What if every single point in the right partition was all crammed down into that one slice? It would still end up being, this is going to be n over 2, but this would still end up being n over 2. Right? We need more structure. Well, if I exploited that structure of distance D away in the x direction, what's to stop me from exploiting that structure in the y direction as well? Right? this point right here, P, if I went up a distance of D, and if I went down a distance of D, that defines a nice little rectangle here that any point that is closer than distance D away to this point right here is going to lie within this rectangle. Right? If it was up here, right, it's already distance D away from the point in the y direction. There's no way that it's going to be closer than distance D in the Euclidean distance sense, right? Likewise, if it lies over here, like for the same reason as before, that it's already distance D away from our dividing line, there's no way that it's going to be closer than distance D to our actual point. Excellent. So here's our little slice, okay? Now here's a much better drawing of it, because I took the time to do it. It's in the book. Where is it? Closest pair, and right there. There it is. All right? There. So if I've got this point right here, x and y, I only need to draw a distance y plus delta up, y minus delta down, and x plus delta, y plus, actually not even x plus delta. If this is my m point right here, then m plus delta gives me the other direction over here. Now, how many points can lie in this little rectangular slice? Can I put like n points in there? What if I pack the points really, really tightly? What if I put like even just 20 points in there? Do I have to compare this one to all those points in there? Can I pack n divided by 2 points in there? No, why? What if I did? What if I packed 2 points in there? Just 2. That one and that one. Tell me about the distance between those 2 points. It's that distance, which I'll call, I don't know, d prime. That's definitely smaller than delta. Why? Because it's inside this square of sides delta. And therefore, I would have found those 2 closer points to begin with, right? When I recursed on the right partition. Okay, so I can't fit 2 points in there really, really close together. So I need to make sure that all the points are at least delta apart. Now, how many points can I actually get it, cram in there before I've filled it up and there are no more possibilities? Well, if you go with the Manhattan distance, which is what the original presentation of this algorithm is in the 1970 or whatever it was paper, I documented that in my write-up, so if you want to check it out, you can. But if you go Manhattan distance, there's 1, 2, 3, 4, 5, 6. At most 6 points. Right? Yeah?
Counting the point itself?
Well, technically what you would do is you would zoom in on this, and the point is on the other side, right? But it's arbitrarily close.
Okay.
Epsilon close. Right? So go ahead and suppose that you do have this point right here. Right? Again, the only argument that we need to make here is that there are a constant number of points. Why? Because that makes our algorithm right here of looking at everything that goes across the border, right? It makes it into an order 1, constant time. Now all together, what do we have? Order n. Meaning that our new recursion is going to be 2 recursive calls on sets roughly half as big, but only a linear amount of work. With our new A, B, and D, 2 and 2, those don't change. But our new D here is going to be 1. So now plug and chug the master theorem. 2 versus 2 to the D, they're equal. So by case 2, what do we have? Order n to the D, but D is 1, so n log n. In other words, basically what it takes to sort it. Right? And there's a hint on the details here. Yeah?
So, why are we doing 2 recursive calls in case we call it?
You have to find you have 2 partitions, right? You have to find the minimum distance in the left partition and the minimum distance in the right partition. You take whichever ones of those is minimum, and then you have to consider everything that's over the border here, or over the split. But ultimately, you get this theoretical behavior here, sub n squared, right, which becomes tractable for, say, 10 million points. Right? It now becomes reasonable to do 10 million points because you're only doing 10 million things times log base 2 of 10 million is nothing, right? That's like, I don't know, well, no, not even 100. It'd be like 20 or 40 or something like that, right? Maybe even less. Right? That's way more reasonable. Right? Now, here's an aside before we get into the details. If you don't like looking at it with respect to the Manhattan distance, we all know what Manhattan distance is, right? So in Manhattan is a grid, right? What is the shortest way of getting from this point to that point? Can you walk through the buildings? No. So to get from one point to another point on a grid, you have to go up that distance and then over that distance. So you can't just, walk through the buildings. And that's why we call this the Manhattan distance, because you're going up and over rather than just jumping over there. Okay? And that's what the original paper had. And that's why and it's easier to argue about this geometrically if you look at this picture. I don't like it because that's not what Euclidean distance is about. And so I took the time to draw this picture instead. Let me go ahead and zoom out there. Right. Now consider this point here. But if you're going to use Euclidean distance, you don't draw a rectangle. What do you draw? A circle. And then half of it is lying on one side. Now how many points can you pack in there? Well, if you draw 3 equilateral triangles, you can end up packing 1, 2, 3, 4, 5 points. Right? Except that they're all on the border in order to get that. Okay? So we didn't buy anything. We went down from 6 points down to 5 points. But if you use some advanced geometry, I'm sure that to pack as many points as you can within this semicircle, this half circle, you have to draw an equilateral triangle with sides delta, and you end up with only 3 points. If you put on the condition that they cannot lie on the border of this thing, then I think that you can get it down to 3 points. That's just a pedantic little thing that always bothered me so much. It bothered me enough to draw this picture and document everything in the actual lecture notes. Don't worry about it. 6, 5, 3, who cares, right? The whole point is that you can get this down to order 1, okay? Now, the details. So, what do we need to do here? Our input is going to be a set of points, S, pre-sorted with respect to their x-coordinates. Now, why are we going to pre-sort them with respect to their x-coordinates? If I'm going to break them up into 2 sets, right, I want to look at the middle right away. I don't want to have to go through and say, okay, well, for each element, okay, you go over there, you go over there, you go over there, you go over there, right? If I'm going to do an order n log n algorithm to begin with, I'm going to sort them with respect to x. And now cutting it in half is trivial. Why? I only have to look at the middle of the list, and there's my cut, right? Now I've got two sets, okay? What about my base case? What should the base case be here? If the size of S is small enough, then use brute force, generate all pairs to solve the problem. Return the pair distance with the 2 closest points. Why didn't I go all the way down to 2? You could, right? Except that, what if I started out with a set of size 5? I'm going to break it into a set of size 3 and a set of size 2. That set of size 3, I'm going to break that into a set of size 2 and a set of size 1. Is that well defined? Nope. So what I'm going to do is I don't want to have to worry about those damn details. I don't want to have to worry about that. So what I'm going to do is I'm going to go, say, down to a set of 20, whatever your threshold is. Whatever your small enough is, right? And you can tune this, right? You can even set this as a parameter and then try out a few things. Maybe it's 100, right? 100 times 100, that's only 10,000 things, right? At most, maybe that's your cutoff. This happens all the time in hybrid recursive algorithms. For example, merge sort or quick sort. In an actual implementation, you don't go down to a list of size 2 and then sort it, or a list of size 1. You go down to a list of, say, size k, right? And then you switch over to insertion sort, because insertion sort on small inputs is actually more efficient in practice than quick sort or merge sort on small inputs. Yeah.
Is there like a math equation where
That would be empirical, right? It's not going to change. The only thing that you're going to get out of math is the base case, and the master theorem will not change. It's going to be asymptotically the same. So whatever your small enough is, right? Whatever that means. Okay. So the first thing we're going to do in our algorithm is we're going to partition S into two roughly equal sized partitions, a left partition and a right partition, according to their x coordinates. If they're sorted, you just jump to the middle and you split it. Right? Then we're going to recursively find the two closest pairs in the left and in the right. We're going to choose between them, we're going to choose the two closest pairs between those. Right? Without loss of generality, suppose that it's of delta d, or of distance delta. Okay? Then what we're going to do is we're going to find the median x value, call it m, right, between the two partitions. That's this picture right here. Right? This m. There's my m. Let's go ahead and clean this up. There we go. There's my m. And then I'm going to go over a distance m minus delta, over a distance m plus delta, and for each point in that left slice, I'm going to look at the constant number of points in the right slice that could give me a better distance, a smaller distance. Right? So I'm going to find that m value, and I'm going to build a subset of S whose x values are m minus delta and m plus delta OA. Right? We're going to talk about the details here in a moment. And then for each point, x in the left slice, compute the distance to each potential point in the right slice. If you find a closer pair, update your closest pair. And again, here's where I'm going to say careful. Right? Careful, and indent there. You cannot or should not compare it to every point in the right slice or the right partition, because that would be an order n algorithm, and master theorem would then tell you that that's going to be overall, it's going to be n squared. Okay? So how do we handle these little details? First of all, let's walk through the actual pseudocode here. This is in the book. You don't have to copy it down or anything, but I copied it so that I could reveal it line by line. First of all, we take care of our base case. If n is the number of points is less than our threshold, then return the closest pair p using a brute force algorithm. Right? That's just for each pair, right? And you're done. Otherwise, next, you evenly split P and L into L and R with respect to the x coordinates. Okay. Let M be the x coordinate that splits the two partitions. And then I recursively find the one from the left partition, recursively find the pair that are the closest in the right partition. Call those AB and alpha beta. Right? PQ will be the two closest pairs between the closest pair from each partition. So in other words, I'm going to do an argmin. Are we familiar with that? The minimum between these two, but then I want the argument of it. So this is 0, this is 1. If the minimum is 1, it gives me 1. If the minimum is 0, it gives me 0. Right? In other words, whatever distance this is. Right? If this distance is less, then PQ takes on the value AB. If this distance is less, then PQ takes on the value alpha beta. Right? Okay. And then I compute delta, which is the distance between P and Q. Let the left slice be a subset of L, the left partition, such that they have x coordinates from m minus delta to that cutoff point, m. Right? Likewise, the right slice will be from m to m plus delta. Now, for each element in the left slice, we do the following. For each element in the right slice with y coordinates, bounded above and below by that delta, we check to see if that has a minimum distance. If so, we update PQ, we update our delta here. And ultimately, we return P and Q. Now, this seems like a pretty straightforward algorithm. The devil is in the details. Right? So, look at this and tell me, how would you go about doing all this? Well, remember that we're assuming that they are sorted with respect to their x coordinates. Right? So how would I end up partitioning it between those two things, L and R? If I've got, say, 10 points, and they're all sorted with respect to their x coordinates, where do I need to cut it off? Length divided by 2, 4. Right? That'd be easy. Right? Okay. That's easy. That's easy. Ooh, maybe this part. Let left slice be the set of all points whose x coordinates are within that range. So be careful here. Can I simply go through all the points and say, are you in there? 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 That would end up being what? Order n. And we're back at square one, n squared. I can't do that. But if all the points are sorted with respect to their x coordinates, can I find this cutoff here? And if so, how? Oh, come on. So, let's think about this number line here. All the points, ignore the y for now. All right, we're just looking at their x coordinates. They're all sorted here. Maybe some are really close together or whatever. Maybe some even have the same x coordinates, but they're different y coordinates. That. Now, I've got m, so it's somewhere right here. And I've got a delta. Right? And I want to go back delta. How do I find all the points within a certain range? Maybe I don't have m. How do I find it? Suppose that all these members have numbers, right? 2, 4, 7, 8. These are all the x values. 10, 10.5, 10.75, 11, 11.5, 12, 13, 14. We'll just keep it simple here. And suppose my m is 9. How do I find that point? Everything that's less than it, everything that's greater than it. How do I find this thing right here? Well, the thing that I suggested before was ask each one. 2, oh, okay, you are less than 9, so you go in the left partition. 4, oh, you go in the left partition because you're less than 9. You're less. Okay, there's the cutoff. You're greater, so you go in the other partition. Greater. Do I have to ask that question of everybody? No. Right? Could I start at one end, ask the question until I get to that cutoff? That's going to be n divided by 2, which is still order n. Can't do that. How can I exploit structure in order to do this efficiently? If it's sorted, how do I find this cutoff? What algorithm can I bring to bear here? Binary search. Right? Start in the middle and say, oh, okay, maybe this is the middle here. All right, and this point here, oh, that's greater. So my cutoff is somewhere over here. Come over here. Oh, this one is less, so my cutoff is somewhere over there. Right? I'm narrowing it down until I find the cutoff. Binary search. Right? So my goal here, that one of the tools I need, right? We need a couple of binary search implementations. The first one I want is, given a set of points or numbers, find and a key, find an element matching that key, or in the event that no such element exists, find where it should be. Now, why do I want that? I want this cutoff. And I chose 9 judiciously here because I knew that it was something not in the set. If my cutoff here was 10, what if it was 10 instead? Then I'd find this and go, okay, well, there's my cutoff. Right? And I split everything over here and everything over here, although I need to decide, is my cutoff over here or is it over here? So I either need to find that cutoff, or failing that, I need to find where it should be. Right? So that I know that everything to the left of this is less than that value. Everything to the right of this is greater than that value. That's how actually most binary searches operate. Upon an unsuccessful search, additional information will be returned to tell you, well, I didn't find it, but if it had existed, it would exist right here. Yeah.
Would they return like a negative index?
It would return a negative index that you would then add the size of the list so that you could know, well, it should be at index 5, but it's not there. Instead, it returned -4 or something. Okay. So there's the first tool that I want to put together here. If we can get this to work.
To make our own.
Yep. Why do we have to make our own if we're going to work in Python, first of all? Is there a binary search in Python? Binary search in Python. Standard library. Yes, there are millions of people that have done this before as a CS1 or CS2 assignment. I would not recommend grabbing their garbage code, right? But if you do, make sure that you test the hell out of it. Right? Binary search. So apparently there's a bisect left Python code. I have no idea if this is correct. Okay, so that's some other library that they're using. Otherwise, it looks something like this. There's another one. But is there a standard implementation? No. Why? They want you to use dictionaries instead. Right? Well, no, you can't use a dictionary on this. At least there's not a clear way of using a dictionary on this. Instead, we're going to have to make our own. So increase the size here. Def binary search. And we're going to take an array and a key, excuse me. Right? And here's my description of what this is going to do. Right? Performs a binary search on the given list, ARR, right? Which is assumed to be sorted. So I'm not actually doing points here. You can adapt this for points, right? For x and y coordinates. But it assumes to be sorted for the given key element. Right? However, this is going to be a little bit different because if no such key element, let me go with the successful search here first. If such an element is found, it returns an index at which it exists. Why did I emphasize un index? There could be 5 8s in there, right? So which one do we, if there are 5 8s, which one do we return? The first one, the last one, the middle one, any of them, right? I don't care. That's not the point of this particular algorithm. It returns an index at which it exists. If no such key element is found, returns an index at which it would appear if it were to be inserted in order. Okay. Let's go ahead and look at an example. And do I have an example here? No, I'm just going to have to make one up. So, I don't know, 4, 6, 7, 8, 8, 8, 8. There we go. 10, 12, 20. Maybe another 12 right there. For example, if our array, a search for, I don't know, 7 would return what? What would we expect it to return? 0, 1, 2. A search for 8 would return 3, 4, 5, or 6. 3, 4, 5, or 6. Right? It could be any of those. Right? A search for 2 would return what? That was, so what? I would, you could put it at -1, but ultimately, if you did insert it, where you have 0 through n-1 again, where would it end up being? 0. That's where you want to insert it. I believe in Python, because of the negative value trick, you could negative index value trick. You could do that as well, right? A search for, say, 25 would return what? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? And just to make sure, a search for 4 would also return 0. Right? A search for 20 would return what? Is it 11?
No,
10. There we go. Value of documentation, right? It tells you exactly what your expectations are, and if we wanted to, we could unit test this and make sure that it actually works. Okay. So first of all, for convenience, let's go ahead and declare a variable n here, which is the length of the array or the list. Right? Let's take care of those edge cases first. Those edge cases being something that's not in there on the left side, something that's not in there on the right side. Right? So if the value is less than the array of 0, or not value, what's my key? Key. There we go. If the key is less than the first element, what should I return? 0. Else if the value at the end is less than the key, right, then what should I return? N. Right. Okay. Now I need to establish my left and right index. Now this is just a standard binary search. My left will start at 0. I'll call it left. My right will start at n-1. Right. Now, while my left and right are less than or equal to each other, they're going to jump in on each other until you find what you're looking for. So while the left is less than or equal to the right, do the following. Right. First of all, I need to compute that middle element. So here's the generalized binary search, right? Here's my array. Here's left. Here's right. How do I get that middle index right there? Left plus right over 2, floor or ceiling, doesn't matter. You tell me about Python though. Can I do this? Left plus right divided by 2. Yeah, well, okay. That's another way. In fact, that's the way I would do it. Why 2 slashes? Yeah, this is going to be like 7.5. Is 7.5 an index that you've ever heard of? Nope. So go ahead and take, well, that's not floor, that's truncation, right? That's integer truncation division that you're familiar with from most other programming languages, right? So if that's the thing I'm looking for, if that's equal to your key value, then return m. I just have to return unindex at which I find it. Right? Again, if I've got multiple 8s here, then it could return 3, 4, 5, 6, doesn't matter. Okay? Oh, thank you. left plus right. And we're good. Else if, right? The value that you're looking for is less than the middle value. Then search left, else, and here I'll go else if the array value is less than the key that you're looking for, then search right. Okay? But do I need this else if? Do I need a last check here? Nope. Right? Okay. Search left. So how am I searching left? I've got a left index, a right index, and I need to search this left half right here. Do I change left? Nope. What do I do to R? I need to move it over here to m minus 1. So R, right, becomes m minus 1. How do I search right? I update to left to be m plus 1, right? Remember, I don't want, I've already looked at the middle element here, so I move left to be m plus 1. Okay? Now, that while loop is going to end up finding an element if it exists. What if it doesn't exist? Normally, like with just a straightforward binary search, I would return none. I didn't find it. Unsuccessful search. But that's not what we want. We want to know if it were to exist, where would it be? For example, here's another example. What about 9? Well, here, 5, 6, 7. Yeah, 9. Let's a search for 9 would return what? It's not in there, is it? But if it were in there, it would be right here. Right? What index is that? 0, 1, 2, 3, 4, 5, 6, 7. I did my counting right, right? 7? Okay. Right? Yeah, it is. Okay. So I'm not going to return none. Unsuccessful search. What do I return? Where it should be. Return the index where it should be. Because this is not found. Not found. Dot, dot, dot. Well, you could do something like Java does and return a negative value there. Right? I don't want to get that fancy, though. I just want to return a value here. So now let's think about this visualization. How did we get out of this loop? Left and right, as long as they're less than or equal to each other, right? Left, right, or they're on top of each other. Left is equal to right, and I'm looking at this element right here. Then we continue searching. How did I break out of that while loop? When left is bigger, in fact, they're right next to each other. Okay? So where does it belong? Between, so right here. This one should move down, right? And we should make room for it by inserting it right here. What index is that? Left. So return left. With our last 7 minutes here, let's test this. I'm not going to set up a full unit test here because that would take too long. Instead, let's just go ahead and say that this is our array. Right? And let's say that our key is, I don't know, 2. And then we'll print result is equal to, the result would be binary search of array, key, and let's output it, result. Come on, cd, lecture, CSE 310, Python demo. So what was our expectation for a key of 2? Should be 0. Good. What about a key of 4? Also 0. What else? 8. Our expectation there would be 3, 4, 5, or 6. Okay, 5. That's good enough. What about another one? 20 would be 10. Oops. Sorry, there we go. 10, good enough. What else? 25, okay. That should be 11, I think. Yep, we said. Yep. A search for 9. Let's do an unsuccessful search, but somewhere in the middle to make sure it works. 7, which is what we said it should be. Okay. Now, how could we use this? Over here in this actual problem, what did I want? I want all points that lie within a distance, right? So given an array, here, let's just outline it here. This is now this is another algorithm that I want, right? Def some other binary search. We'll figure it out next time. But here's what I want. Returns a pair of indices, I and j, let's say, such that all values in the array list lie between the two, lie within the range given. Right? The range, say, x or lower to upper. Right? So if you gave me two numbers, right, lower and upper, I will find the index for the first one. I will find the index for the second one so that you know that all of these numbers lie within that range. What is that going to look like, by the way? It's just going to be two calls to the function that I just made. Find this one, find that one, right? There are a little bit of details that we have to work out because of corner cases like this. What if it returns 5? Is that and so I give you this element right here. Is that going to contain? Is that going to give me the range containing all 8s? Nope. I have to shift this down to over here. What if it gave me? There are a couple of other corner cases that we have to figure out. For example, what if it was from 8 to 25? Right? Would it work on the other end? Would it work on this end? Right? How do we deal with? Usually, what we deal with is inclusive, exclusive kind of things. And so, do we want to follow that pattern, or do we want to follow a different pattern? And that's where we'll pick it up next time. Hey, whoever's online. Any questions on this so far? Otherwise, I'm convinced that this works. I've got a unit test to prove it if you want to see it. But uh-oh. Oh, well, we're not going to call it that. We're going to call this a range binary search or something. I'm going to leave it. Right. That's a terrible function name. You shouldn't be embarrassed to call something like that. We're going to come back because I wanted to describe it and then we'll name it. Right? Documentation first and then you start naming things. All right. Next time.